The robot worked perfectly in the lab. For months, it navigated hallways, avoided obstacles, and followed commands with precision. Engineers tested it again and again. Every sensor reading was clean. Every movement was controlled. Every metric looked promising. Inside the lab, the robot appeared intelligent. Then the robot was taken outside. Within minutes, it failed. It hesitated. It drifted off course. Then it stopped completely. Nothing was broken. No hardware failed. No software crashed. The robot simply could not cope with the real world. This is not an unusual story in robotics. In fact, it is one of the most common lessons engineers learn. Robots do not fail because they are poorly designed. They fail because the real world is unstructured, unpredictable, and noisy. Inside the lab, conditions are controlled. Lighting is consistent, surfaces are flat, sensors receive clean data. The robot's environment closely matches what it was trained and tested on. Outside the lab, everything changes. Sunlight interferes with cameras. Uneven ground affects balance. Dust, reflections, shadows, and moving objects introduce uncertainty. Robots rely entirely on sensors to perceive the world. Cameras, lidars, inertial units, and force sensors convert physical reality into data. Control algorithms assume this data is accurate, timely, and complete. When it is not, the robot does not question it. It acts on it. A small error in perception becomes a small error in motion. That error feeds into the next control cycle. Over time, errors accumulate until the system becomes unstable. This is called error propagation. Humans compensate instinctively. We adjust our balance, ignore noisy signals, and adapt to changing conditions without thinking. Robots do not. They execute exactly what the model predicts, even when the prediction is wrong. Another challenge is generalization. The robot learned patterns from its training environment. When the environment changed, those patterns no longer applied. This is known as distribution shift. To a human, the outdoor environment was still a hallway, just under the open sky. To the robot, it was an entirely different world. This is why robotics is not just about intelligence. It is about uncertainty. Real autonomy requires systems that can detect when their assumptions are failing, adapt to new conditions, and recover safely. Most robots today cannot do this reliably. That is why many robotic systems still operate in warehouses, factories, and controlled spaces, not because engineers lack ambition, but because reality is difficult to model. The robot did not fail because it was stupid. It failed because intelligence alone is not enough. Robotics is the challenge of turning mathematical models into physical behavior in a world that refuses to behave mathematically. And until robots can handle uncertainty as well as humans do, the real world will remain their greatest test. If you want clear, grounded explanations of robotics, artificial intelligence, and emerging technologies, subscribe to The Intelligent World, because understanding how technology works is no longer optional.